Hello everyone, this is Narges from Salzburg Research Ltd and also University of Salzburg. I would like to present our recent accepted paper in the Symposium of Applied Computing 2025 conference. So the paper is about PreMatch. It's called PreMatch, a prediction-based scheduling for data flow, asynchronous processing, and the computing continuum. It's a collaboration with Zahra from University of Innsbruck, Samira at that time University of Twente, Radu, a professor of AGI at University of Innsbruck, Frank and Peter from Salzburg. Frank is a professor at the XDG project, which is the main funding support for this work as well. And Peter is the head of the Intelligent Connectivity Department at Salzburg Research. As I mentioned, this work has been funded by XDG project, which is a project supported by the state of Salzburg for bringing the vision of the digital science and interdisciplinary technology into the community. So first I will introduce the main topic. I will present the main motivation behind this work. I will present briefly the architecture, the overall architecture of this work, including the models for the machine learning and replica scheduling, and then it will be followed by the prediction-based scheduling, including the replica side and the device side-based prediction-based scheduling. Then I will present the prediction and scheduling experiments, and then I will conclude this presentation. The recent shift towards the microservice-based application, the computing continuum, has introduced the workload prediction challenges. For instance, at what time do we need more amount of microservices to be deployed? And also including the scheduling challenges. So at which time we need to consider that the resources are needed to be released so that the other microservices can be hosted by the computing infrastructure or the devices, such as edge devices, or the deployment challenges. For instance, to use the pre-deployed cloud instances or not to have a fresh deployment at the edge, or maybe the orchestrator, such as, for instance, the ones that are currently addressed by third-party tools like Kubernetes or Nomad by HashiCorp, other tools for macOS, for instance, by Apache. This work is an extension of our two previous works, or it's better to call an integration of them. One of them, as you observe on the left side, is about the call rate prediction for replica estimation. By considering that we have a feature set consisting of the microservice call rate and then microservice time, then we apply some machine learning models over that. We optimize the hyperparameters, we get a trained model, and then at the end, we use this trained model to predict the number of the call rate prediction and then the number of replicas. This was integrated more or less in the data cloud project. It was a new project which this tool was responsible for adaptation of the data pipeline execution alongside the definition, the simulation, and then the deployment engine. From the other side, we had developed this scheduling, which is called PreMatch, which was responsible for scheduling the microservices or placing the microservices at a specific time throughout the time execution of these services over the computing devices. This was based on the matching-based theory principles, which is a game theory approach, and it was presented in the proceeding and also published in the proceeding of the IEEE cluster conference. So, what about the PreMatch? PreMatch, as I said, is the integration of these two works. It has from one side the feature sets such as the microservice time, microservice call rate, and also the number of replicas, which are used to predict the number of replicas. And then from the other side, the scheduling is responsible to say that at which time each one of these macro replicas that have been predicted to be passed to the orchestrator so that later on they would be deployed on the cloud, fog, or edge instances. And also we are using this, we are relying on, I would say, this monitoring system that regularly captures the information in regards to the application execution, and alongside the microservice analysis requirement, this replica prediction is telling us, for instance, how many replica for each one of these microservices we need. More specifically, the feature set that we used as the input, we consider the multiplication of the microservice time and call rate, and then as the output, as an extension of our previous work, we predict the number of replicas. And then alongside the hyperparameter tuning and later on the trained model, we use this analysis of each microservice that the end user or the producer of the data submits for deployment on the computing infrastructure. We predict the number of replicas for that, and then the scheduling first tries to rank the replicas for the devices, and then also the devices for the replicas, and applies a matching-based approach for scheduling of each one of these predicted replicas on the infrastructure. Let me say at this level, through an example, that how this replica, predicted replica, actually is going to be calculated. So assuming that here we have two different microservices, one microservice is M0 that is deployed on D0, and it takes almost 0.7 seconds per call per request of the producer, and per second it receives 3 different calls. The other one is microservice 1, which is scheduled already initially on device 1, and then it requires 1.5 seconds per call to be executed, and per second it receives 2 different calls. So looking at this maybe diagram, we can observe that having just one replica of microservice 1, therefore until the end of the 2 seconds, just 3 calls have been processed or have been satisfied. Although until the 2 seconds, we have 6 different calls. That's why the idea was here to add another maybe replica of the same microservice so that it can concurrently execute the different calls and then satisfy the requirement of the producers. Therefore, we came up with the solution that maybe having the multiplication of the microservice time and then microservice call rate can help us to come up with the proper number of replicas. So using this formula, we are thinking which one of these machine learning models would be suitable for us. As you are aware, we have 2 different machine learning models, 2 different types. One of them classification, the other one the regression, which helps us to come up and predict and estimate a specific value regarding to a dependent variable based on the input, number of inputs that we pass to the machine learning model. Here in the category of regression models, we explore 2 different models. One of them is the multi-layer perceptron, which is from the category of neural network or current neural network, and it has the forward propagation and back propagation. And as you observe, we have two different layers. The first and the last one are the input and output, or the output is the predicted value for us. And then the hidden layer consists of three different neurons. However, we also applied the other type of model, which is the gradient boosting, which constructs an additive model in a forward stage-wise manner. As you can observe, for instance, we have a data set. It divides the data set into different parts or subparts, and then each part is responsible to applying a model or a tree-based model over that. And as you observe, each stage passes the output of itself to the next stage in order to use the weak learner from the previous stage to improve the next stage prediction. And then it combines all the weak learners to improve the performance of the overall model. Let's see how we have been using this model, and then what was the performance of our method based on this. As I said, we use the prediction output, which is in terms of the number of replicas for each microservice. And then we apply the scheduling. The scheduling model is based on a matching. From one side, this can consist of the replica teams, and then from the other side, it consists of the device team. The replica team ranks the devices based on the macroservice time, and then the device team ranks the replicas based on the transmission time. I mean, in between any two interdependent replica, how much time does it take in order to transmit the data for the start of the successor macroservice or upstage macroservice. So substitutedly, I will call maybe the replica as the macroservice and vice versa, but every replica is showing the same property of the microservice, just as the repetition of it in order to support the different calls of the users. Okay, as you can observe here, we have two different weighting parameters. One of them is alpha, the other one is beta. So when alpha is 1, so that the goal is to increase the profit of the replica over the other team's profit. Here, we also applied the profit of the other team over the replica team. And then we call this type of a scheduling model the device side or transmission time optimized scheduling. So here we set beta 1, and which the goal is that this team wins the other team so that and its matching would be more prominent to the game. To evaluate the model, we used two previously developed microservice-based applications. One of them was the video processing application, receiving a specific, for instance, scenes or segment of a video captured by camera movie, pre-recorded. And the other one focuses on the text processing, considering that we have a specific data set submitted by the producer, and then it's annotated most probably, and then we need to apply different microservices over that in order, for instance, to give a score to a specific test data of the producer. In regards to video processing application, this one specifically focuses on object recognition for roadside inspection, while the other one focuses on the sentiment analysis extracted from the Amazon reviews on the Amazon website. For the computing infrastructure, we benchmark the execution of the aforementioned microservices and the replicas on this computing infrastructure. As you can observe here, it's a snapshot of the edge devices interconnected to the exascale cloud instances located in different regions based on their provided data centers, one in Sofia, the other one in Frankfurt and Vienna, which these two data centers for us were considered as the fog instances, and Sofia for us was considered as the cloud instance because we were mainly located at the time of benchmarking these microservices in cloud. And then also we had two other type of devices, single board computers, such as the Jetson Nano and Raspberry Pi devices as the edge devices. For more information in regards to this edge infrastructure, I would like to attract your attention to the following papers. One of them generally talks about and presents the cloud fog and edge computing infrastructure of C3 or the Corinthian computing continuum, and then the other one more specifically targets the edge devices and presents an automated mininet compatible SDN testbed based on the Raspberry Pi and NVIDIA devices. How about the historical data for the machine learning models? We were relying on the microservice traces from the Alibaba cloud. No need to talk about the Alibaba cloud. For sure you are familiar with that. We were focusing on these traces, specifically the ones that in between the microservices, they were having a message queuing interface in order to transmit the data in between one another. Although the trace was consisting of different types of communication in between the microservices, such as, for instance, the inter-process communication, or the remote invocation calls, or in terms of the stateful services, they were having the databases or memory cache. Based on the features that we had previously, I mentioned the multiplication of the microservice call rate and microservice time as the input, and then the number of replicas as the output. We polish the data set and then we reach a specific number of records of this trace that would show the correlation between the two feature among these feature sets. The data set is available publicly on Zenodo, and then we use a specific library, mostly the Python libraries, in order to implement our not only machine learning model, but also for data processing and also the matching-based game. The result of the prediction shows that the GBR model basically can predict and can fit the model into the test data with a lower error in comparison to the MLP multiplier perceptron, which basically fits more or less a linear model. Okay, as you know, the performance of the neural network-based models, here we just use one layer of neurons, although in terms of increasing the number of neurons or the layers, making the model deep enough, we can probably optimize the model. However, we wanted to reach a fair performance in terms of the training time in between these two models. So, because at least up to this level, based on these settings, the GBR or the gradient boosting regressor reaches a lower error. Therefore, we use the predictions from the GBR in order to pass it to the scheduling model and then predict the number of replicas and then later on to schedule it throughout the matching-based principles. As I presented in the previous slides, we used two different scheduling models, or method is better to call. One of them was the replica side to optimize the microservice time, and then the other one was optimizing the device side. The performance was more or less, in terms of the completion time, close, I would say. And we also compared the results with another machine learning based and prediction based scheduling model, which here was relying on the NLP machine learning model for prediction of the the workload, and then ILP for scheduling of the microservices over the computing infrastructure. The completion time here is the basic metric that we evaluated, and because mainly the microservice-based applications that we developed and then we benchmarked throughout our work were more compute intensive and CPU intensive. That's why the performance of, I would say, the replica side scheduling model is better than in terms of the completion time than the other. Okay, coming to the conclusion, in this presentation, I had the basic strategy behind the prediction-based replica scheduling model, which was more or less relying on machine learning models such as the gradient boosting, which is a theory-based machine learning model, and it predicts the number of replicas for us for each microservice, and then its results show a closer performance to the actual data. We reached a lower completion time for PreMatch in comparison to the other methods, and then for the future work, we also plan to develop and improve and extend these works towards presenting a green scheduling based on considering the energy efficiency while finding the proper and appropriate solutions for scheduling the microservices and its replicas over the computing infrastructure. Thanks for your attention, and feel free to contact me in the case that you have any questions in regards to this work.